We're going to continue to talk about series. And what I want us to talk about now is estimating series. i.e., using partial sums to approximate series and knowing how good the approximation is. Now, this actually depends on the series that we are looking at, so I'm going to tell you about ways that we can approximate particular series, and then maybe I'll do a few silly examples, but we're actually going to do this again in a couple more sections, so you'll see more examples later on. Who first? Maybe alternating series. That's nice. Okay, so let's suppose we have some alternating series. So we have series minus 1 to the n of an, and goes from 0 to infinity. Your an positive, so that you have alternating signs. Then recall our Sn. This is the sum of the first n terms of the series, so this is a0 plus a1 plus a2 plus an minus 1. Or just to make it nicer, just start this from 1 and go up to n, just to make it a little bit nicer. The formulas I'm going to write down. Now, the entire series is going to be a1 plus a2 plus a3 plus, going on forever, and if we take the difference between the two, so I take S minus Sn, this is going to be equal to pretty much every one that's left over after I subtract this from that. So that's going to start at an plus 1 plus an plus 2 and an plus 3, and that's going to continue. This guy here, our notation for that will be R sub n. And this is called the remainder term. So basically, it's going to be the difference between the actual sum of our series and the approximation of the sum by the nth partial sum. So the difference between what the actual answer is and the answer we get by adding up n terms, this is called the remainder term. Now, it turns out for an alternating series and for several kinds of series, we actually know a lot about this guy. And it's Calc 2, so I can't prove at this point how we know all these things. I'm just going to tell you what we know. For the alternating series, it turns out that the size of the remainder term it actually has a very nice relationship, i.e. the size of S minus Sn is actually bounded above the difference between the actual answer and the answer I get by adding up the first n terms is going to be bounded above by n plus 1 term. So it turns out that in an alternating series, if you add up a bunch of terms, the size of the very next term is actually going to tell you how close you are to the actual answer. Which, might seem a little bit crazy, but that's actually true. So, example. Look at this alternating series. So this guy gives us -1, yes, plus a half, minus a third, plus a fourth, minus a fifth, plus a sixth, minus dot dot dot. We know this converges, right? Alternating series test. But what if I wanted to approximate what does it converge to? Well, at the moment we don't know how to actually calculate what that actually converges to, but I can kind of know how good a certain approximation will be. So for example, I can ask a question like, how good an approximation is S4, let's say. So if I add the first 4 terms, how good is this compared to the actual answer? So that could be a question I could ask. And the answer will be the following. So S4, you don't need to say this, but just as an FYI. S4 is going to be equal to -1 plus a half minus a third plus a quarter. Now, if you were to actually add all of those, 12 is the LCD. You'd have -12 plus 6 minus 4 plus 3. And what's that? Minus 16 plus 6, that's minus 10 plus 3, that's minus 7 over 12. Right? So you might say, I just added the first 4 terms and the answer I got is 7 over 12. How close am I to the actual answer? Turns out all I have to do is look at A5. A5 would be 1/5. This means we are within 1/5 of the actual answer. In other words, the actual answer to this series, i.e., the actual sum of this series, is going to be between -7 over 12 plus 1/5 or -7 over 12 minus 1/5. The actual answer is somewhere between those two numbers. And of course, you might have, that might be for whatever reason too big of an error for whatever purpose you're doing. So all you do is you add a few more terms until that window that your answer should be in actually closes to within a gap that you can actually use. So that's with the alternating series. Very nice. The sum of the first n terms, how close that is to the actual answer is approximated by the very next term, by the n plus first term. So how close is the sum of the first 4 terms? Well, the 5th term tells you the answer. How close is the sum of the first 100 terms? The 101st term tells you the answer. How close is, if I add 5,223 terms, then 5,224th term is going to tell me how close I am. So that is true for the alternating series. So the actual answer is somewhere between those numbers. Here is another question that I could ask for the same series. How many terms are needed to approximate the sum with say 0, 0, 0, 1 accuracy. How do you think I would do that? I want to get to within 4 decimal places of the answer. How many terms do I need? What do you think? Yeah?
You have to find when the term is equal to 1,000. When the term is, it would equal the term before the term that equals 0.0001.
Okay, so how do I find that term? Yeah?
Maybe you could just equate it to -1 h divided by divide by n equals to 0.0001.
Divide what by 0, 0?
You see that equation
Yeah.
on the left, like -1 to the power n of n. You could equate it equals to 0.0001. You can find n.
Sure, pretty close. That's not the one we want to use though. Yeah.
Well, you know that 0.0001 is 1 over 10,000,
Mhm.
and you know that the number at the bottom is always 1 less, or the number at the bottom is equal to the n. So if that's 1 over 10,000, and you want the one before it to find within that accuracy, then it'd be 9,999.
I'm not sure why you keep saying before. It's after, right? So say
Well,
n plus 1.
Yeah, but
You're-
that's
you're-
the n plus 1. So it's over 4 over 1, right?
Yeah, so here's how to answer the question. You actually want, you pretty much want the difference between the nth partial sum and your actual answer, which we know is less than or equal to an plus 1. I want that number to be less than or equal to that. Alright, so the n plus first term I want to be less than or equal to this. That's going to guarantee that this difference is less than or equal to that. And so pretty much, in this case my an is 1 over n, so in this case I want 1 over n plus 1 to be less than or equal to that. In other words, this means that 1 over n plus 1 to be less than or equal to 1 over 10,000, which basically means, flip this, you know that there's the inequality sign is going to turn around. This means n plus 1 must be greater than or equal to 10,000, or my n must be greater than or equal to 9,999. So, to get this level of accuracy, I need to hit 9,999 terms before I get an answer that's this close to what the actual answer is. So let's say I'm fine, whatever I'm using, it can't deal with accuracy higher than that anyway, higher than 0.0001. Whatever machine I'm using only goes up to 4 decimal places anyway, so I really don't care about what the numbers are after the 4th decimal place, or maybe even after the 3rd. What I can do is instead of adding up an infinite number of terms, I can just have a computer add up 10,000 of them. Once it adds up 10,000 of them, we will actually have whatever that number gives us. I don't know what number it's actually going to give us, but I know when it gets to that point in the series, I will have 4 decimal place accuracy. So that is with the alternating series. You can approximate it pretty easily. The n plus first term tells you about the approximation of the first n terms, how close you are to the actual answer. So that's nice. What other tests? Some of them are too complicated. I don't want to tell you about everything. Maybe the integral test. The integral test, that one's nice enough. So let's say you use the integral test to use the integral test to determine if something converges. Okay. How good is this approximation? So again, the Rn and Sn, same notation. It turns out that then your remainder term, we actually know a bound for that remainder term. It is actually going to be the integral from the nth point of the series to infinity of f of x dx, and the lower bound is going to be the n plus first term of the series of x dx. It will be, the remainder term will be between these, where ax equals f of x, and we're considering the series. An goes from, say, 1 to infinity, or whatever. So if I were to add up, say, 10 of these terms, how good is that? Well, I would just do the integral from 10 to infinity, and that will be an upper bound on the remainder term. So if I want to know how close I am to the actual answer, so in this case, the actual sum is going to be between Sn plus this integral, the integral from n to infinity, and Sn minus the integral, well, Sn plus this integral. The actual answer will always be between those two. So if you find the nth term, so remember your Rn, this makes sense because your Rn is equal to S minus Sn, and so I can add Sn to both sides, and I get this. So the actual answer is going to be between these two values. If you add up the first n terms, add to it the integral from n onwards, and add to it the integral from n plus 1 onwards, and those are the upper and lower bounds for your series, and that will actually approximate your series to a certain number of terms. So, is there a nice one that we did here? Okay. So, for example, we used the integral test to show, we looked at this series from 1 to infinity of e to the 1 over n over n squared converges. That was the kind we did. Yes. So we might ask, I might ask you the question, after you prove that this converges by the integral test, how good an approximation is, say, S5. Right? If I add the first 5 terms of this thing, how close am I to the answer? So what I could do is I could come, so here, this puts me at the 5th term. So I am going to actually do the computation, the integral from 5 to infinity of this guy, e to the 1 over x squared dx. And this is, I think you want the limit as a bit. I mean, at this point, we kind of know how this is going to work out anyway. 1 over x squared dx. Essentially here, you do a u substitution, u equals 1 over x, and so you'd end up with the integral of minus e to the u du, and you'd get minus e to the u, and being a little bit sloppy here, I just want to get through this. So this is minus e to the 1 over x dx, between 5 and n, as my n is going off to infinity. So if I plug in n and let n go off to infinity, this goes to e to the 0, which is minus 1, plus plug in 5th, e to the 1/5. And that's how close I am. Error will be less than this. magnitude-wise. That's the integral test. So if I ever ask you, okay, prove this converges by the integral test, how good is your approximation if I used 5 terms, or 100 terms, or whatever? You would simply just find that integral. Integrate from that point on, and your error bound will be that or less. That's the integral test. So a problem like this will be like part B of some series problem. So you'll deal with a certain series problem, and then I might ask you, how good of an approximation is this? Or how many terms do we need to get it to be this accurate? And this is kind of like an afterthought. It's not an afterthought, it's an important question, but in Calc 2, how I would ask it, it would be like an afterthought. I'd have you do all this stuff with series, and then, oh, by the way, if I only added 100 terms, how good is it? Or how many terms do I need to get the accuracy to 0.001? I can ask things like that. That's the integral test. Okay, ratio test, gonna skip that one. The comparison test. Ooh. Do I want to tell you about the comparison test? Because the comparison test kind of depends on what you're comparing it to. I'll talk about comparison test. So the comparison test, it's kind of finicky. It depends on what you're comparing it to. So if you're comparing it to a series that you can know converges by the integral test, you can use this. If you're comparing it to a series that is alternating, you can use the alternating series version. One common thing that we always compare things to is using the p-series. That's a very common thing to compare things to. So suppose I use a comparative test to show that something compared to a p-series converges. Then set Bn to be the p-series we converge to. And if Bn B of x equals f of x, then it'll actually look a lot like the integral test. The remainder term is going to be lower than that. It looks very similar to the integral test because you can actually use the integral test to show that the p-series converges. In fact, how we know about p-series was using the integral test. We integrated 1 to infinity of 1 over x to the p. And we used the integral test to prove the p-series test. So a very similar thing holds true for the comparison test whenever you compare it to a p-series. We literally integrate the p-series. So let's say I compared it to 1 over n cubed. Then I can just integrate 1 over x cubed on this interval, and that's going to give me the error bound. Ratio test we're going to skip. That one is too complicated. I'm probably not going to ask you that. But yeah, those are estimating series. Like I said, this is going to come in handy later on. I'll just say it in passing, and we're going to use it later. What I really want to talk about today is 11.8. So we went through 11.3 to 11.6. 11.7, oh, maybe I should talk about 11.7. Did I tell you the strategies for doing the series? Okay. 11.7 is about strategy, so it's a general kind of section. So again, as you guys probably realize, sometimes it's kind of hard to see which series test you might want to use for an arbitrary series. So there are some strategies that you might want to do. So 11.7 talks about the strategies, and then in its section it just gives you a random assortment of series and have you, hey, try to use the strategies now, see if you can recognize which series to use. So probably mention that before moving on. So given a random series. How to determine if it converges. So, first thing you probably want to do is try test for divergence. So you're always going to check this, and basically if the limit of the AN is not equal to 0, we know right away it diverges and you don't have to do anything. It's probably always one of the first things you want to check. 2. Check for specific forms of geometric series have a very specific form. Okay, so this means if it looks like A times R to the n, and it goes from 0 to infinity, A are constants. Then it's geometric. Another very specific form that should jump out at you is the P series form. That means your series look like 1 over n to the P. So things like that should really jump out at you. Maybe, probably even before the test for divergence. If you see something that looks like this, it's just a constant base raised to a power n, or 1 over n to some constant power p. So those you can recognize pretty quickly. So that's probably the second thing you would look for. The third thing is probably if an is easily integrable. And of course you have to check positive continuous decreasing, and try the integral test. For if an is rational or sufficiently close to being rational, something like the radical of a rational function or something like that. Try P series, try comparison test. Where you usually compare to a P series. Alright, another thing you would look for is if an looks like some formula raised to the n, you may try the root test. If an has factorials or more complicated exponentials than just the nice nth power there. Try the ratio test. Another nice one. Alternating series. Just squeeze that in here. Alternating. That's a nice one to notice. Alternating. So these guys look like the signs just alternate, -1 to the n of, say, the n. You'll notice those. So yeah, pretty much for an average series, especially if it looks ugly, maybe the limit might look nicer. It's nicer to just look at it as a limit. If your limit does not converge to 0, then it automatically diverges, and you don't have to do anything. Certain specific forms should pop out at you, things like alternating series, piece series, geometric series. If those forms show up, you should see it right away and apply those tests. If the thing is easily integrable and is decreasing and continuous and all that good stuff, you can try the integral test. If it's rational or something close to it, probably comparison to a p-series is going to work. Remember, if you know for sure which way the inequality turns, just do a direct comparison. If you're not sure which way the inequality turns, you would use a limit comparison test. If you have a nice power of n, the root test would be good because that allows you to take the nth root and get rid of the nth power. And if you have a bunch of factorials and stuff, maybe more complicated exponentials, like there's an n squared power and an n plus 2n plus 1 power or something like that, you would try the ratio test. And probably 7th, I don't know if this is position 7 exactly. I mean, some of these just go by what you're seeing. Might be telescoping. And for this class, you'll know that you'll look at this especially if asked what the series converges to, because it's not very often that we'll actually know in this class how to calculate what it's going to converge to. So if I say, oh, prove the series converges, and if it does, show what it converges to. So say you get a complicated rational function, and you're like, okay, I can know it converges pretty easily, I'll compare it to a p-series. And you say, oh, it does converge, and then I follow up with like, what does it converge to? Then chances are it's going to be telescoping, use partial fractions, break it up, and figure it out. If it's a geometric series, that's also easy to know what it converges to because you have that nice formula, a over 1 minus r. The other ones, though, we don't really know what they converge to. We just know yes or no, it converges. What the series converges to. So there are only a few cases where you'll actually be able to calculate things. So if there's a problem like that, if it converges, tell me what it converges to. Chances are it's going to be geometric or a telescoping series, unless it's a power series question, which we will talk about power series soon. Yeah, okay. So that's the general strategy, kind of what to look for. In terms of that table that I had you guys fill out, I would probably actually give you that table, so you probably don't have to memorize it. But the table I have. Yeah, so that would be the strategy, and hopefully you guys were working on some series this weekend, so you probably kind of figured this out already, but just in case you didn't see any patterns, here are some patterns to look for. Now I want to talk about power series. Very important topic. 11.8. Power series. So one of the most important things you can actually do with a series, like it's right up there with integration itself. Right? So remember, integration comes to us as a series called a Riemann sum. So like half of calculus is built on us knowing that a certain series converges, called the Riemann sum. But right up there, just as important, is the idea of a power series, which is a little bit more general than a Riemann sum. It's more general than calculus, so this is something that is applicable, even if you're not in a calculus context. It's a very important idea. So we're going to talk about power series for a little bit. And I'm going to show you how to derive some and a general method for finding a power series when you aren't given one. Definition. A power series is a series of the form. So it's a series with a very specific form, and this is the form. A-N, do I want to use A-N? Probably C-N. Just might use A-N for something else. A-N and B-N I usually use for something else. X minus X naught to the N. N goes from 0 to infinity. This is called a power series. It has that form specifically. So this is the power series. We call it centered at X naught. About X naught. So X sub 0. The CNs are constants. Given by some formula dependent on n. So I know that probably is kind of weird right now, but basically Cn is going to be a formula in terms of n, but for each particular n, you're going to plug in into this formula and you're going to get a constant. So all the Cn's are going to look like constants. X is the variable. Usually we want a real variable, x in R. You can extend this to complex variables, and you probably can even extend this series going down to negative infinity. But for us, it's going from 0 to infinity. X is just a real number variable. N is just going to be integers from 0, 1, 2, 3, counting up. And for each such n, I will be able to compute a coefficient to the variable x. This guy, Cn x minus x naught to the n goes from 0 to infinity, would look like this. C naught plus C1 x minus x naught plus C2 x minus x naught squared plus C3 x minus x naught cubed plus dot dot dot. If x naught equals 0, say, so a power series centered at 0, basically this would look like n equals 0 to infinity of Cn x to the n, which is going to be C naught plus C1x plus C2x squared plus C3x cubed plus C4x to the fourth plus, which reminds you of what?
Geometric series.
Good, yes, but also lower level. Too complicated. But yes, it does remind you of a geometric series. We're actually going to use that to our advantage, actually. Just a polynomial. But a polynomial of infinite degree, if such a thing could exist. It turns out that there are going to be cases where such a thing will exist. I can talk about, oh, there's this polynomial that has infinite degree. And you're like, how does that even make sense to even talk about? Well, it makes sense if this series converges. So, pretty much the goal is we're going to learn a lot about power series, and the idea being I am going to want to be able to express different functions as power series. Why would I want to do that? Well, maybe the function is really nasty to work with in a certain context. However, if it were a polynomial, it would be super easy to work with in that context. What I can do, the next best thing, if it's not a polynomial itself, maybe I can express it as some form that's similar to a polynomial. Such a form is called a power series. So it's pretty much when you're expressing something as kind of a power function, right? X to the n is the power function. So this is a power series. Okay, so pretty much like an infinite degree power function. Anything that looks like that, I call it a power series. So your C0, C1, C2, C3, these are all numbers once you expand it. There will be a formula that will tell you how to calculate those numbers. The x is your variable. That is called a power series. Now, do I do an example here, or do I want to actually talk a little bit more about the power series? Let's do some more definitions and then I'll do an example. I'm going to give you a theorem first and then talk about this. Theorem. Let boom boom Cn x minus x naught to the n equals 0 to infinity be any power series. Then there are 3 cases for its convergence. There are only 3 situations you can find yourself in with a power series. 1, it converges only for x equals x naught. Okay. So sometimes the Cn's are going to be numbers such that this infinite polynomial is not going to make sense. Pretty much the only way I can get this expression to make sense is if I plug in x equals x naught. Notice what that will actually do. It will make this 0, that 0, that 0, that 0. Everyone is going to be 0 except the first term potentially. And so the series will just sum to the very first term. That's just going to be a number. That's going to be fine. It'll make sense for that. No matter what the C's actually look for, if they're just numbers, plugging in x equals x naught wipes everyone else out, and I'm just left with the first number. Similarly here, x naught equals 0, plugging in x equals 0 kills everyone else except the C0. So that's going to make sense. That will converge to something. So that's one possibility. 2. It converges for all x in R. So it's possible that I have some formula like this where no matter what I plug in for x, it's going to actually work. It will create a series that actually converges. We'll see examples. Or 3. The series only converges on a particular interval for x's. This interval can be expressed in the form x minus x naught is less than r. Okay. So one thing I want you to notice is if I write an expression down like that, basically because of how absolute values work, this means that, which basically means that my x will be below r plus x naught and above x naught minus r. So there will be a window on the real line where this series actually makes sense. If I'm outside that window, it doesn't make sense, but if I'm inside that window, it will make sense. R is called, so that's the end of it. Right? For any power series, there are 3 situations. It will converge only for x equals x naught. It'll converge for any x that I plug in, or there are a specific few x's that it will converge for, and the x's that it will converge for will obey an inequality that looks like this. R is called the radius of convergence. Or abbreviated ROC. And we need to check if the series converges at the endpoints of this interval. So it's possible that it will converge at the actual boundary, so I can put an equal sign here and an equal sign there, but it's possible not. So we have to check specifically if it converges at the endpoints of this interval. And the interval where it converges is called the interval of convergence. Which I'll abbreviate IOC. Here's one thing you can note. Note R equals 0 in case 1. Okay. R equals infinity in case 2. Okay. So, for a power series, there can either be 0 radius of convergence, it literally converges at a point. There is no radius. You can't move to the left or the right of that point. It will converge at that point only. Radius of convergence is 0. It will converge on the entire real line, which means from that point I can move an infinite distance to the left and it's going to work. I can move an infinite distance to the right and it's going to work. That means R is infinity. Or there's going to be some window. It will only converge for x's between these windows, on this window. In that situation, I know that it will converge in that window, at least if I have open intervals here, but I have to specifically test the endpoints. It might converge at this boundary or that boundary, but I'm not going to know unless I specifically test it. So this is where your convergent tests are going to come in handy. This is kind of why we need them. The big deal is the power series. We want to know how to talk about these guys, when they work, when they don't work, and that's why we did all the series convergence tests in the first place, to be able to talk about power series. We want to know where these guys are going to work, where they will actually give us a meaningful polynomial of infinite degree. And that in and of itself is going to be extremely useful. Emily, you have a question?
It's just making sure the IOC is referring to the second.
Yeah, the interval of convergence. We're going to actually do an example. So it's actually talking about the window.
Yeah.
And the radius of convergence is the length of half the window.
Yeah.
So in case 1, pretty much what's happening is on the real line, this is the real line, you converge at that point x0. Series works here, nowhere else. In case 2, then you have on R, pretty much the series works everywhere. Series works everywhere. And so if I choose some point to center it around, I can talk about the radius moving off in that direction, and it's infinitely long. And in case 3, it only converges on a certain window. So this is the real line. My x0 is here. There's a point that I can move in this distance given by x0 plus some radius of convergence, and I can move back this distance given by x0 minus some radius of convergence, and we may or may not converge at the endpoints. That's checked separately. And so this is the distance r, right? From the center, how far can you move to the left or the right? Turns out there will always be a symmetric interval in which it converges. The interval will either be of length 0, or length infinity, or length double this value. But at the actual endpoints, I don't know if it converges ahead of time. I have to actually do that check. So that's a very important theorem for a power series. Now, there is some mercy here in Calc 2. You'll always use the ratio test to determine the convergence. This is true a lot of times outside of Calc 2 as well, but there are some times outside of Calc 2 where you have to get a little bit more sophisticated. But if I ask you, hey, here's a power series, find its interval of convergence, or hey, here's a power series, find its radius of convergence, you're always going to do the ratio test every single time. Okay, so that's not like a strategy, oh, I have to figure out, what do I have to do now? No, it's always going to be the ratio test. So at least there is no figuring out that has to happen. Let's do an example. Find the radius of convergence and interval of convergence of the following. Here is a series, x to the n equals, let's say 0 to infinity, series. X minus 4 over 2n to the n from 1 to infinity. C, the series, and it goes from 0 to infinity of x to the n over n factorial. So here's some power series. Notice here my Cn is given by the formula 1. Here my Cn is given by the formula 1 over 2n. Here my Cn is given by 1 over n factorial. So these are all power series. Now, where do they work? So, let's look at the first one. N equals 0 to infinity of x to the n. If I want to find the interval of convergence or the radius of convergence, what should I do? Huh? You're too shy. You need to talk to me.
Ratio test.
Ratio test. It's always going to be the ratio test. Okay, so find the radius of convergence of blah. It doesn't matter how scary it looks. You're going to do the ratio test. Always the ratio test. So here you're going to check that you're going to find the limit as not check. I mean, consent is implied. You have to force the limit of an plus 1 over an to be less than 1, right? That's when the ratio test actually works. So what I'm going to do is I'm going to look at this entire thing here as my an. I'm going to take that, I'm going to put in this formula, I'm going to compute the limit, and then I'm going to force it to be less than 1, okay? Now, if I can't make it less than 1, then the answer is it only converges at x equals x naught. If it's always less than 1, and it doesn't even matter what I pick for x, then I say the radius of convergence is infinite. However, if there's only a window of x's where it's less than x1, I can use this expression to actually figure out what that window is. So that's what we're going to do here. So here, I'm going to have L. This is going to be the limit as n approaches infinity. It always approaches infinity for sequences. And so here, it's going to look like x to the n plus 1 divided by x to the n. That simplifies. That's just the limit as n approaches infinity of x in absolute values. Now, what's the limit as n approaches infinity of this?
Infinity.
No. It's just itself, right? There are no n's. So it's kind of like you're taking the limit of a constant. So what you're going to do is you're going to set this less than 1. and that automatically gives you your radius. You can think of this as a power series centered at 0, therefore this is kind of reminding you at x minus 0 less than 1, and that's telling you that's exactly the form for the radius of convergence. So I know that this implies that the radius of convergence is 1. So there's actually a window. Notice x less than 1, well this means that x is between 1 and minus 1. So now, to find the interval of convergence, for interval of convergence, we're going to check the endpoints. So, we're going to look at x equals 1. Okay. So what happens at x equals 1? I'm going to go to the original series, I'm going to plug in x equals 1. So the series would become 1 to the n equals 0 to infinity. Tell me about that series. Converges or diverges? Why?
Because it's 1 plus 1 plus.
Sure, it diverges. The nice way to see, or to just be able to justify, test for divergence. Right. The limit of an is 1, which is non-zero, so that diverges. What about at x equals minus 1? Then what series you're going to look at is minus 1 to the n equals 0 to infinity. And so that's going to be 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. It also diverges, because it never actually hits 0, much less settles there. Diverges, test for divergence. So this means the interval of convergence is the open interval. So the radius of convergence is 1, and it does not converge at the endpoints. Because at the endpoints, I get series which diverge by the test for divergence. However, if my x is between minus 1 and 1, let's say I plug in x equals to a half, and I write out this series, it will actually converge to a number. X equals to 3/4, write out this series, it'll converge to a number. X equals minus a half, write out this series, it'll converge to a number. As long as I'm within this window, not including the endpoints, and I plug that in for x, this series will actually give me a meaningful answer. It will give me a finite answer. So that's bonus. What does this converge to? So if I'm looking at this series here, x to the n goes from 0 to infinity, what does it converge to? If x is less than 1 in absolute values. What do you think? Yeah?
The root test?
Root test doesn't tell you what something converges to. And you're never going to use the root test. You always use the ratio test to determine convergence for a power series. There are only two guesses, really. There are literally only two series that we know how to actually say what they converge to. What's one of them? Just throw out one of them.
Geometric?
Geometric. Does this look like it could be geometric?
Kind of, yeah.
What would not make it geometric?
The fact that it's not like a constant dx, the
Oh, but in terms of the series,
Then yeah, it's geometric.
yeah, the series, the n is the variable for the series.
Right.
As far as the n is concerned, x is a constant. I have nothing to do with x. It is actually a geometric series. This is geometric. My a equals 1, my r equals x, which is constant in relation to the series. That's going to be a big thing in multivariable calculus. There are going to be times when you have all these variables all around, but sometimes you think of all of them as constants except this one guy. That's going to be a big thing. So get used to that, right? In terms of our series, n is the variable, x is a constant. Once we actually evaluate this power series as a infinite polynomial, we might want to think of the x as a variable in that situation. But when this series is repping it out, x is a constant as far as that series is concerned. Which means, what would this look like?
What do you mean?
What is the answer?
Oh, the convergence.
I know it converges, but to what?
Like a over 1 minus r.
A over 1 minus r, what does that look like here?
A over 1 minus x. Or 1 over 1 minus x.
1 over 1 minus x. Now, i.e., I feel like my heart just skipped a beat. The gravity of this statement should not be lost on you. I basically just told you, looking at the function 1 over 1 minus x, I can actually write that as an infinite polynomial. Whenever I'm in a certain window. Now, there are some issues here, obviously. This formula has an asymptote and all sorts of things going on with it. If I want to differentiate it, I have to use chain rule and all sorts of crap. However, if I think of it on this side, it's a polynomial. Continuous everywhere. Everywhere being within the window minus 1 to 1. This guy is often going to be much easier to deal with than that guy. So this is a power series, and in fact, I can actually think of this as that function. I can add up an infinite number of terms that look like this, and what does it add up to? That function. We're going to do more of that pretty soon. Pretty soon you're going to create power series for random functions. We're going to know, how do you write sine x as a series? I'm going to teach you how to do that. How do you write cosine x as a series? I'm going to teach you how to do that. What's ln of x as a series? I'm going to teach you how to do that. And you might want to know, well, what would the point of that be? Well, we're going to see when we do it. So that is a geometric series, and that's what it adds up to. It adds up to some function. Let's do B. So we have something that looks like x minus 4 to the n over 2n, and goes from 1 to infinity. How do I find the radius of convergence and interval of convergence? The ratio test. It's always going to be the ratio test. So I'm going to look like we employ the ratio test. Sometimes you have to make it look nice. So L here is equal to the limit of x minus 4 to the n plus 1 over 2n plus 1 times the reciprocal of the original 2n over x minus 4 to the n. This is going to cancel into that. So pretty much I'm going to have the limit of 2n over 2n plus 2 times x minus 4. What's that limit?
X minus 4.
X minus 4 in absolute value. Now I'm going to set this less than 1 because that's what I need for convergence. And so that again tells us, well, the radius this again tells me the radius of convergence is 1. Now, since x minus 4 is less than 1, this means minus 1 is less than x minus 4 less than 1. This means if I add 4 everywhere, this means my x is between 3 and 5. Now, for interval convergence, IOC, check endpoints. So, what happens when my x is 3 and what happens when my x is 5? So I'm going to look at x equals 3. I'm going to go to the original guide. I'm going to plug in 3 for x. 3 minus 4 is minus 1, so this is like minus 1 to the n over 2 to the n, and goes from 1 to infinity. Converges or diverges?
Does it converge because you can compare it to the alternating harmonic?
Oh, well, you don't need to compare it. Converges by alternating series test. You can do the alternating series test directly on this guy. Your a in here is 1 over 2n. That's decreasing. And the limit equals 0. So that actually converges. So at x equals 3, it actually works. Okay, what about at x equals 5? Well, I'll go to this original series and plug in 5. And I would look at 5 minus 4, that's actually 1. 1 to the n is 1. So it's like 1 over 2n, and goes from 1 to infinity. Converges or diverges? Well, converge, diverge? Any guesses? Yeah?
It diverges
Why?
because it's p series and it's n to the 1 and
Sure.
it's just a
Diverges. It's
just a
harmonic.
constant.
Yeah, so p series with p equals 1. It's harmonic. It's actually the harmonic series. I can like factor out a half, and I get the harmonic series.
Yeah.
So it diverges. So what does that mean for the interval of convergence?
X equals 3 is included.
So it's x values between 3 and 5, where the 3 is included, but the 5 is not. So it actually converges at the left endpoint, but not at the right endpoint. And for all x values inside that interval, it actually converges. Moreover, there's another important thing we get about the ratio test. What does the ratio test actually give us? As in terms of the kinds of convergence. Absolutely convergent. So whenever anything converges using the ratio test, we know it's absolutely convergent. And that is going to be very important. We'll actually pick up with why that's important next time. So what I would suggest you do, try that with this guy. Try to see if you can find the radius of convergence and interval of convergence for him. And then we'll pick up with that next time. But yeah, for these guys, you're going to need to know your convergence test really quickly because that's not going to be the point a lot of times. It should be, in a couple seconds looking at the series, you should know if that converges or not. So be sure to know that table. We'll stop there.